A giant of the sea roams the ocean, a huge ship with a massive crane. This is the Oleg Strashnov, one of the biggest monohull crane ships in the world. Its mighty boom is able to lift up 5,000 tons of weight. It is not only a huge crane, but also an efficient multitasker, integrated into a ship system that stays stable in the water, whatever the weight, whatever the elevation. This is a true marine monster, a legend of the sea. The sun rises over the Dutch port of Schiedam, located on the busiest waterway of the country, west of Rotterdam and close to the open North Sea. This is where a hub of nautical companies provides the most advanced engineering support for the whole of the maritime industry. GustoMSC is one of the oldest offshore design and engineering companies of the country, and it is where the world's largest and most advanced nautical cranes are built and integrated into ships that are also designed here. The glass and steel interior of the headquarters has been grafted on a building that was once home to the company's competitor when it was founded a century and a half ago.
We see the ship and the jackup, but together with what we call the mission equipment, like cranes, we see that as an integrated design, which basically the purpose of this type of ship is not so much sailing, and the purpose of the ship is to perform a heavy lift.
That's where it starts with. Is it for a ship, or is it for a jackup or a semi? That already has a big impact on the type of crane and for the design.
The name of GustoMSC is intimately tied to the world of shipborne cranes, machines that have played a fundamental role in the offshore energy industry for decades. Little-known machines that have been strategic for the growth of first oil and then the wind farm businesses. GustoMSC's clients are companies that, amongst other things, require heavy lift capacity offshore. The cranes that the company has designed are integrated into ships, jackups, and rigs that not only navigate the seas but also have necessary stability to withstand the environmental forces and perform their heavy lifting tasks. Arjovan Putin is the chief engineer of the crane department at GustoMSC. He has honed his skills on designing massive cranes of all types, including the huge 5,000-ton crane of the Oleg Strashnov installation ship.
Lifting capacity is one of the most important things, and the outreach, in fact the combination. So for example, if it is 5,000 ton at 30 meters or 40 meters, that's really a big difference. Once we know that, then it is important also to know the lifting height, especially nowadays for the wind turbine installation cranes. Then the required lifting height increases quite a lot. So that's also an important factor, and it can also have an impact on the complete design, what we are going to use.
Alain Vassink is the marine architect who designed the Oleg Strashnov and is now sales director for the GustoMSC cranes.
GustoMSC is a design and engineering firm, and we specialize in design of mobile offshore units of all sorts and types, from jackups to semis to ships. The company started out as a shipyard already in 1862 and has made a lot of different things in the time, but it has pretty quickly specialized in heavy-duty workships. Floating cranes already started in the 1900s, and dredgers and other ships And especially from the 60s to the 70s, it started to specialize in the offshore industry.
We have a couple of main components in the crane. So that's the foundation of the crane. Then you have what we call the slewing platform. So everything is mounted, everything that rotates with the crane is mounted on the slewing platform. Then we have the boom itself, and we have the A-frame. In most of the cases, can be a tower as well. And all the ropes are going through via the A-frame to the boom. And it depends on the loads on those main components. So we have an in-house developed program, software, which we use to determine the loads on those main components.
The massive crane that Ariane and Arjo have built is the result of 7 years of hard work, first designing and then building and testing the ship and crane.
It was in the spring 2007 that we got the order for the delivery of the crane. Then we spent about a year on the whole design, and then of course already we start purchasing materials because there are some long lead items, especially in that time the market was booming, so delivery times increased quite fast. So we ordered all the long lead items as soon as possible. Then the eventual delivery was almost 4 years after we had the original order.
Yeah, so we started out already in 2005 with the owner, CWF Lifting, to come up with a concept for a fast crane vessel. Most of the vessels are quite slow, 4 to 6 knots at that time. Fast crane vessel, versatile, with the then highest lifting capacity for monohull in the world. And they wanted to have a design that could sail fast and be very stable when doing lifting operations, which usually is a contradiction.
While GustoMSC actually builds the cranes itself, ordering in the parts from outside, the company provides the ship designs to third parties who construct the ship. The two key elements of the integrated ship and crane system grew by the day until the ship was ready for launch. It was the 22nd of August, 2009.
I've been involved since the inception of the ship. Seeing it enter the water was quite an exciting moment. It's for me as a naval architect, that's the birth of the ship.
This is the Oleg Strashnov. The massive ship is 183 meters long, 47 meters wide, and has a draft of 13.5 meters when working. However, when sailing, the ship has a reduced draft of 8.5 meters and reduced beam to give it greater speed than any of its competitors. Oleg Strashnov is one of the largest monohull crane ships in the world, and the original owners had some specific and very ambitious requirements for the ship. Indeed, it was and remains a revolutionary ship in many ways. It is one of the fastest of its class. It has one of the largest cranes, and above all, it offers an amazing amount of versatility. It is truly a marine monster to be respected.
So the ship came out at a little over 180 meters in length, with 2 beams, of course. So we have 37.8 meters on the low draft, and we've got 47 meters on the deep draft. And to make this happen, you need quite a high ship, because you have to still have some freeboard when you're in your deep draft. So you're at around 18.2 meters in depth of the hull, with ultimately a displacement of around 70,000 tons at the deep draft.
The marine architects of GustoMSC accepted the challenge to design a ship that was highly unconventional, but also highly competitive in terms of speed and, of course, fuel consumption. The design criteria for the Oleg Strashnov included the ability to work on site, while the ship also provided a stable base for the massive crane with its unique revolving main hook with a 5,000-ton lifting capacity. Designing such a ship maintaining balance when the crane arm is fully extended was a challenge.
We developed a very special hull shape with them, which is a patented hull, which has a dual draft, where you can have a small draft, where you have a narrow hull, so less resistance, which is quicker, less fuel consumption, but less stable. And when you do a heavy lift, you need a lot of stability, but no speed. So you can go to a deeper draft, and then the ship is much wider and has more stability.
Main characteristic is that it can lift 5,000 tons. It does it at an outreach of 32 meters. The maximum overturning moment is at another distance. That's 3,800 tons at 43 meters. The lifting height is approximately 100 meters above the main deck for the main hoist. And there's also an auxiliary hoist, which can lift about 30 meters higher. That has an 800 tons capacity.
Oleg Strashnov, however, not only had to have one of the biggest cranes on the high seas, but also the widest range of lifting capacity. So Arjo introduced a unique design into the crane, a crane within a crane.
There is a trolley hoist with a lifting capacity of 30 tons. It can travel along the boom and it can lift 30 tons. But yeah, we didn't want to just add steel to integrate that. So what we did, we made in fact a fifth core boom. So there's a fifth core in the middle, and we create so we have 5 cores to really transmit the whole load. So that's a bit special. And in that way we could design quite a light boom, even with this integrated trolley hoist. If you use the trolley, you can keep the boom at the same angle, and the trolley just moves along the boom. So you don't have to move that slow boom, but you can just use the trolley. That works quite fast.
Once the design phase was over, the ship and crane could be constructed. The day came when this monster had to be built, and Arjo and Ariane worked together to deliver one of the most amazing and least celebrated ships plowing the ocean waves. In particular, the lifting part of the unit required some of the most innovative construction techniques. Everything is massive.
The boom chords, for example, so the big tubes are made from 690 material. That's steel with a strength of 690 megapascal. And also other parts like in the A-frame, the backside, mostly parts in tension, are made out of the 690 yield material. But for example, the braces, which are welded, the tubes in between the big chords, are made of 355 yield material, because they are not governed by the stress in the material, but by vortex shedding.
However, most of the crane's work is done with small loads, and this is where the supplementary lifting machines come into play.
Well, a special thing about this crane is that, normally when the crane is rotating with an empty hook, with a boom at about 60 degrees angle, the CUG is exactly in the middle. That was one of the design criteria. There is a removable ballast system at the backside of the crane, and by doing this, then most of the operations are actually small loads. So the lifting capacity is 5,000 tons, but I think more than 90% of the lifts is less than 100 tons. And during all those operations, the boom is at approximately 60 degrees, and it can rotate without having to ballast, because the center of gravity is in the slewing center.
The industry sets standards, but these cranes are so huge that extra safety measures have to be introduced to make sure nothing, absolutely nothing, goes wrong. There are several main component parts of a crane. The boom, the long arm that extends out to sea to lift heavy loads, and of course, the A-frame that controls the extension of the boom. lifting and lowering it as necessary, and through which the lifting cables pass. There is also the ring platform around which the crane swivels, and the motor that provides the power both for moving the crane and turning the winches that pull the loads up or down. On Oleg Strashnov, all these components are massive. Oleg Strashnov's A-frame is also special, as the client required the ship to pass under the world's bridges, such as the Bosphorus Bridge that joins Europe with Asia, so as to engage in offshore heavy lift in the Black Sea, one of the world's most strategic areas for energy resources.
We added an extra hinge at the aft side of the A-frame, so at the back leg, which is a vertical leg. Normally that leg is in tension, but during transit of the vessel there can be a vertical load downwards as well, and then it's in compression. What we did is we created an extra hinge, which is normally locked by a small beam, and when we want to lower it, first the boom is lowered into the boom rest, and if we keep on rotating with the boom hoist winch, then the rope tension is lowered, and eventually the A-frame should go backwards, but you have to help it a bit. So what we did is there is a locking system, and when you unlock it, there is a hydraulic cylinder, and it gives us what we say a kick in the knee, so it starts to bend, and then on its own weight, it has to go backward.
Once these major design features were established and construction completed, the actual assembly of the massive crane began. This in itself was a mega-lift operation. The motor housing was built in China and delivered to the Schiedam docks, where it was to be integrated with the ship. Here it was lifted onto a massive barge and lifted by two shear legs to be transported to Oleg Strashnov. The motor housing had to be positioned with millimetric precision, and only the expert eyes of the designers and construction workers could guide it properly into place. It was placed delicately on the base and the pin. The bogies followed and were fitted perfectly on the rails, allowing smooth rotation of the crane. Then the A-frame had to be fitted. Not only the static part had to be precisely connected with the crane base, but the folding segment had to be lowered so that the massive pins that allowed it to be collapsed to reduce height could be inserted accurately. This, in itself, was a mammoth task, and yet there was much work still to be done. The largest single element of the crane was now ready to be moved. The heavy lift company, Sarans of Rotterdam, moved the boom onto a barge using self-propelled mechanized transports, or SPMTs, from which a massive shear leg was able to lift the 100-meter-long steel trellis structure onto the huge hinges that awaited it on the crane body. This was the crucial moment of the assembly of the whole Oleg Strashnov crane ship. This was followed by lifting the ballast for the crane, the counterweights that are brought into play every time the boom lifts a weight at the fullest extension. The next stage involved the reeling of the cables and ropes. Dozens of steel cables were pulled through the boom guides and then meticulously wrapped around the winches. The closer to the core of the winch, the less cable is released, so the automatic gears are key to keeping lifting speed uniform. The 64mm cables had to be guided by special ropes through the boom all the way to their winches, one by one, and wound on accurately, secure. This is the heart of the whole crane, where the lifting actually takes place.
Yeah, from the client we receive certain lifting speeds. So they specify a lifting speed, an average speed, because if you have the winch, there are several layers of steel wire rope on the winch, and so the rope speed is different when you are at the, let's say, the 10th layer or the first layer. So they specify an average speed, so that's where we are working with. We calculate the required power.
Now that the crane had been constructed and installed on Oleg Strashnov, the next crucial stage could begin. Oleg Strashnov is the largest monohull crane ship in the world and flaunts three very special characteristics that other ships of the same type do not enjoy. It's fast, its crane can lift 5,000 tons, and it is incredibly versatile. On the 11th of March of 2011, the ship was ready to be tested. The crane capacity was the first requirement that had to be tested. The trolley crane was put to the test. This was done by filling balloon-shaped containers with seawater and simply lifting. Once these tests had been completed successfully, the onboard computer system could be calibrated, providing accurate load readings. The next test phase involved putting the secondary hook through its paces. Now came the moment for testing and calibrating the 5,000-ton crane. To do this, the crew filled a whole barge with water, and the main hook was lowered to lift it. Not only did it have to lift the weight of the barge and water, but, just for good measure, an extra 500 tons. The crane successfully lifted it and swiveled with it to put the structure to the test at all angles. The crane passed the test with flying colors. The ship was now ready for sea testing. So let's take a tour of the Oleg Strashnov as it is today. These photographs allow us to see the inner workings of the offshore workhorse. This is the view from the crane driver's seat. The whole length of the ship is now visible, with the hundreds of pieces of auxiliary equipment on it.
From the crane side, it's you have lifting tools, all kinds of tools that you use to actually pick up the load, rotate the load, control the load, to put it into, once you put, for instance, for a wind turbine, you put the monopile on the seabed, you need to keep it in place, otherwise it falls over. So there's a gripper that keeps it in place. Then you need a big hammer that is actually lifted on, and that's also a couple of hundred tons, the hammer alone. And that is all the equipment for the lifting operation itself. Then for the positioning you need the ROVs, so the remote-controlled robots underwater. Surface diving is still used. It's amazing how much equipment fills up the deck when you do such an operation.
The main hook was specially forged as a single block just for this crane.
The crane is electric powered, so it receives power from the vessel. The vessel has generators, and we receive 6.6 kilovolts from the vessel. It's about 6,500 kilowatts is the power that we maximum consume. And in the crane, at the backside, there's 3 levels of electrical equipment. And there it is transformed to 690 volts. And we have rectifiers. They make from the AC, they make DC. And then we have drives who convert that power to the motors at a certain frequency and speed.
Special safety features ensure that accidents with the winches are practically impossible, including clamps on the cables, sensors that stop the hooks from impacting the top of the crane. The crane is also designed to be able to operate in harsher weather conditions than its competitors.
When the hook is hoisted towards the boom, we always know the exact height of the hook, and when it's coming close to the boom, there is a warning. When it comes a bit higher, it automatically stops and there is an alarm. And when there is the warning, it already goes to a lower speed. When there is a situation that the crane operator wants to go even higher than that, he can overrule that, and there is another safety switch at the boom which stops that motion, and that cannot be overruled anymore. And that's the whole crane. Everything is safeguarded by at least two systems. If one fails, then the other one still is there as a backup.
The boom and hook are not the only areas of the ship that can go wrong. There is a double braking system on the cables, and winches too that can hold loads in place if there is a danger, or even lower them slowly if power is lost.
These winches have a double brake system. You have a system on the drum itself. That's for a holding brake and for emergency. And there is also a brake at the gearbox. So there is the motor that transfers the load to a gearbox. And so that's the high speed. And then one of the intermediate shafts is used to mount the brake. And there was a bit of a special request in this case, because we also needed to do emergency lowering on those brakes. So in case there is no power available, we need to be able to lower with the brakes the load.
Oleg Strasnov has a class 3 dynamic positioning system, which means that it can stay in location with movable thrusters, but it can stay in location even after a fire in one of the engine rooms. So it's got redundant engine rooms, redundant thruster rooms. A total installed power is needed of 27 megawatt, divided over 6 generators, 6.6 kilovolt high voltage distribution system, which is top end for this type of vessels.
Keeping the ship stable and perfectly positioned to accurately lay the foundations of oil rigs or wind turbines in extreme weather conditions is an essential requirement for a supply ship like Oleg Strasnov.
There's a lot of positioning equipment. It's not only GPS, they also use pre-located sensors that are put in the field to get the exact right location. That is for wind turbines, but that's also when you're installing big jackets for offshore oil and gas. That needs to be pretty precise. And there's a lot of specialized equipment used. GPS is only one of them.
Keeping the ship on site is done by anchors attached to cables that can be pulled to move the ship one way or the other.
In addition, what we included was a mooring system, an 8-point mooring system, which is also used a lot. These are 8 big mooring winches on the 4 corners of the ship, and each winch with a 15-ton anchor. So we are able to keep her in position in quite heavy conditions.
The same is true for crane movement, as every change in the ship's center of gravity has to be compensated for.
When we do have a big load, indeed the vessel needs to ballast. So there is a ballasting system, and it pumps a lot of water from one side to the other side. So for example, when we do a test load with 5,500 tons, to make one revolution, we do it very, very slowly, because the crane can do it in 3 minutes, but the vessel needs to pump a lot of water to the other side all the time. So one revolution takes then about 1 hour instead of 3 minutes.
The ballast system on the crane vessel is one of the key systems that you have on board, because you have to keep the ship upright and you have to compensate for the crane. So the crane is revolving and the ballast system has to compensate for all the loads that act on the hull, and it's a ship, so it moves. And in this case, with this kind of crane, with a large outreach, you need a lot of ballast capacity. So the ship has around 50,000 cubic meters of ballast capacity, and it has a pumping capacity of 20,000 cubic meters per hour.
The true power of the crane lies in the motors that power the winches. They are 6,000 kilowatt engines and have redundant backup systems just in case they fail and a heavy load has to be brought down gently. This is the heart of the crane system. The cables operate 4 different cranes positioned along the boom: the smaller 30-ton crane and the massive 5,000-tonner. This is the huge ring built to allow the bogies to swivel the crane. This too is powered by the electric motor, which is supplied by the ship's generators. The crane could not operate without the ship. This is the engine room, where the engines can push the ship up to 40 knots, as fast as many of the cruise ships that plow the seas today. The expansive deck has a capacity of 10 tons per square meter and covers an area of 3,500 square meters. At last, Oleg Strashnov was ready for operations. Its extreme versatility allows the ship to perform all the operations involved in building an oil rig or a wind farm. This animation shows the phases of laying the foundations of a wind farm control center. First lifting the foundations and positioning them on the sea floor, and then moving the structure itself, using the 2 hooks on the crane to right the steel structure and position it onto the foundations. The really heavy lift comes with the upper platform, a monoblock of drilling and living areas, all less than 5,000 tons. The ship's versatility allows for it to carry out many operations, and this in turn reduces time on site, generating significant savings for oil companies and wind farm builders. The whole new source of energy is developing all around the world, and this ship has the ability to supply the wind turbine market optimally. Offshore wind farms maximize efficiency and can be bigger than those built on land. The size of the individual wind turbines that must be installed on the seabed is also growing.
It was designed to do operations for the oil and gas business. But the first job it had after it was finished was the installation of monopiles for quite a big wind farm. And they were very successful at that, at CV Heavy Lifting. And afterwards, the majority of all the work they have done with the vessel is for installation of foundations for wind turbines. They also did some interesting oil and gas jobs, but yeah, the market changed quite a lot in that period.
In these images, we see the phases of wind turbine construction and how the massive 5,000-ton crane is suited to the task. The ship is able to lay both the foundation and the mast, and then the turbine itself, all in sequence.
When we designed Oleg Strashnov, we were looking at offshore oil and gas, and then you do a heavy lift, and that is one project, one heavy lift. In offshore wind, every day you do a heavy lift. It's like an industrial process. And that means that you have to be highly efficient in doing the lifts. And Oleg Strashnov is one of the vessels that have been very efficient in that. And that is mainly, of course, the operator, Seaway Heavy Lifting, that has been doing that, but we are a bit proud of that ourselves as well.
The Oleg Strashnov sails off onto another assignment as the offices of GustoMSC in the port of Schiedam are closed for the night. There is no shortage of work for these new versatile crane ships. The future for seaborne heavy lift has never looked brighter. Another day at the port of Schiedam, Netherlands, the heartland of the nautical industry, a hub for nautical services worldwide. This is where GustoMSC enables and supports safe and efficient operations at sea. The Oleg Strashnov crane ship has inspired other vessels, including the Hiyang Shigyu 201, which was built in China based on GustoMSC design, and also mounts a 4,000 metric ton capacity crane and a pipe laying system able to lay rigid pipelines in 2,000 meters of water. In the energy business, mono-hull ships are not the only solution, however. So the company has designed several jack-up rigs that are more stable than ships when working at sea.
There's a clear difference in foundation installation and turbine installation, where especially the foundations are getting bigger and heavier, but they can be installed by ships, which are usually can be easier built with larger cranes, while a jack-up is more stable, less movement especially, and is very well suited for turbine installation because of the fragile parts.
When we delivered the vessels and the cranes for wind turbine installation, the size of the wind turbines was for 3.5 megawatt till 5 megawatt. At the moment it's 8 till 9.5 megawatt, and the expectation is that will grow in the first, let's say, 5 years until 15 megawatt, and beyond that probably even to 20 megawatt. So there is more or less no crane capacity available in the world to install that.
Rather than just design another very big crane, we looked at, okay, how can we make a smart solution that also better fits the jack-up, because otherwise the boom starts to stick out 30, 40 meters, which is highly impractical. So we explored the telescopic boom crane, and of course they exist in land cranes, but also that's a capacity that's nowhere near what we're doing here, because we're talking 1,200 tons plus capacities. So we developed a new system for this telescopic crane, and that's what we're proposing to industry now for this next generation of turbines.
And we have focused mainly on the telescopic crane, which can be retracted. Then it can lift quite heavy foundations, but you don't need the high lifting height. And in extended mode, it can also lift the turbines and the blades, and then the load is lower, but it's still about 1,200 tons. But you need a lifting height of something like 160 meters above vessel deck, so that's really, really high. We have a truss boom, and what we do, we extend it using a reeving system, and when it is extended, we have pins which connect the extendable part with the base boom.
The company also supplies smaller cranes for oil rigs, as well as a unique hydraulic jack-up system that is currently used on oil prospecting rigs the world over. The company is growing in the Far East market, and the Fushuan Sangsha Mani jack-up oil exploration barge has a 1,000-ton capacity crane. However, GustoMSC is also working on a new division of versatile cranes that may change the face of heavy lift for decades to come. One of the jewels in the crown of GustoMSC is this mini crane built to be mounted on the leg of the rig to provide especially fine lift. Named after a crab's claw for its crab-like grabbing motion, the Chila can reach below the cantilever and elevate toward the main deck, providing crane access to areas that were traditionally blocked by the drilling cantilever. By being able to work in this area, Chila has significantly reduced total well construction time. And in the energy sector, time is money. This crane, with its multifunctional claw arm, is also special because it can easily be taken apart and remounted and retrofitted for different jobs. But it also is making repair work on platforms out at sea safer for workers by literally lending a hand in narrow, small spaces. By separating wireline operations from the drill floor operations, Sheila effectively reduces human interaction between the different crews doing different jobs.
We have also put a lot of effort into what we call the round-the-leg cranes. They are specifically developed for the jackups because you have the 4 legs that are sticking out, and you want to be able to have as much freedom with the crane as possible. So the logical thing is to put it around the leg, which had been done before, but nowhere near the capacity that we were doing. So that was really a first off that we did for our round-the-leg cranes around the late 2000s. Of 800-ton capacity.
The wind blows constantly across the dunes of the Netherlands' northwest coastline. Just offshore, wind turbines are being laid to create some of the largest offshore wind farms in the world. The Dutch are world leaders in this sector, and Oleg Strashnov is poised to capitalize on this rapidly expanding new market. As demand for energy continues to surge, oil exploration will continue in the petroleum-rich North Sea, and dependence on renewable wind energy is also likely to expand, creating many new opportunities for these kinds of versatile marine cranes. The sun sets on the port of Schiedam, the heart of heavy lift in the Netherlands. This is where ships have been built for centuries. This is where cargo has been handled by traders in the great Dutch tradition for centuries. Nowhere is more suited to the development.
3, 2, 1, top. Allumage Vulcain. Allumage des 2 EAP et décollage vers 244.
The Ariane 5 launcher shoots into space. Its rockets not only pushing its own weight in metal and fuel, but also a high-tech payload. The launch is the culmination of decades of development, experimentation and research in engineering and ballistics. The 2 lateral boosters weigh 227,000 metric tons each when full of fuel, the equivalent of more than 15 towers of Pisa. They are 30 meters tall. Each one provides 6,000 kilonewtons of thrust, 6,000 times the force of gravity, and pushes more than twice the weight of the launcher and its payload. This is just the beginning of the Ariane 5's voyage into space.
That's why rockets are dangerous, because they are, by nature, they are very explosive.
Reaction, which was found by Newton in 1687, okay, is you expel something behind you fast, and the faster you expel it and the heavier what you expel is, the more reaction you get.
The most exciting moment, and this is the reason why we are having that profession, is the first time you launch a new launcher, or the first time you launch a launcher on which you have had a key role in the design of it, or for my case, this was in the change of the flight software, rebuilding the flight software of a launcher.
The Ariane rockets were developed in France, but draw on almost a century of experimentation and research worldwide. Europe's rocket scientists began with simple, unreliable machines. One of the founding fathers of modern rocketry, the Russian Konstantin Tsiolkovsky, discovered the propellant power of liquid hydrogen and oxygen. In 1914, the American Robert Goddard proposed multi-staged rockets, solid fuels, and the use of the Laval nozzle, narrowing at the waist to accelerate the hot gases to supersonic speeds. In Germany in the 1920s, Hermann Oberth studied rocketry and proposed that rockets could be used to explore interplanetary space. But when the Second World War broke out in 1939, all Germany's rocket science was put to building wonder weapons. Wernher von Braun led the rocket program based on the Pomeranian shoreline at Peenemünde. It did not change the course of the war, but it opened a new chapter in space exploration when Wernher von Braun moved to the United States under Operation Paperclip, while other top German scientists were taken to Russia. Wherever they were made, rockets were, at first, powered by extremely volatile propellants. One of the world's foremost aerospace journalists is Bernard Chabert from France.
In a rocket fuel, you have two components. You have the propellant and the oxidizer. The propellant can be kerosene, just like on the first stage of Apollo, for instance, and the oxidizer is something which helps burn. And chemically, when you have this mix between a very raw fuel, propellant, plus a very basic but nevertheless violent oxidizer, the more violent it is, the more powerful it becomes.
Engineers have learned from the many mistakes of the last century to produce the reliable, fine-tuned rocket engines of today.
Mechanically speaking, it's a nightmare. And then you bring them into a combustion chamber where they have to be precisely mixed, more precisely than any cocktail in a bar. It's really it's pure chemistry. You're working at the extreme of metal capabilities. You are going to really try to break something and stop just before it breaks. You have to gimbal the thrust, and this is done. It's just like cutting flowers. It's really something very precise, and it's almost a work of art in terms of guidance.
Russia's own rocket genius, Sergei Korolev, began the Soviet Union's own rocket program, developing first the Sputnik satellite, kicked into orbit by an R-7 rocket, and then the first manned spaceflight. By 1959, Russia had landed a vehicle on the moon and sent a satellite around it. Russia was winning the space race, and the United States had to respond.
The Russians built the number of R-7, Semyorka, they made is absolutely staggering. It's tens of thousands, because they used it for military use as ICBM, and they used it to launch Gagarin. They launched the Sputnik with it, they launched Laika with it, and today we are launching, Europeans are launching Semyorkas from Kourou, because that rocket is is so dependable and so predictable and so easy to use that it's still in use today, and it's more than half a century away.
Outside the Soviet Union, only the United States had the ability to launch satellites. European nations came together to attempt to launch their own rocket, but it was a disaster.
British came with the Blue Streak missile, which was a strategic missile. The French came with Véronique, which was a small rocket, but which had evolved into technologically comparable rockets. And everybody came with its own little thing, and they stacked the thing together, and they called it Europa, and they brought it to Australia and pushed the button, and the thing exploded in billions of little pieces.
The French space agency, CNES, Centre National pour les Études Spatiales, is located in the heart of Paris, and Christophe Bonal is senior project manager. He has been involved with the Ariane project since the beginning.
We developed a satellite, brand new satellite, together with our German colleagues called Symphonie. This was in 1974. And so we had no mean to launch Symphonie. And so we asked the Americans, could you please help us and launch our satellite? And they said, yes, okay, yes, sure, no problem, you're welcome. With one condition only, please don't make any commerce from this after. Just keep it experimental and don't do any commercial activity out of this. And then we thought of it and said, no, oh, whoa, no, thank you, we'll do it on our own. And so this was a decision for the development of a brand new family of launcher.
The Americans, with their position regarding telecom satellites, created in Europe and more specifically in France, created a kind of reaction, and some of the French said we need to be independent in terms of launching capacity. We need to develop our own system, despite the fact that we've just missed the thing with the Europa experience. And that's how they got together. At the same time, they developed the idea of ESA.
The European Space Agency brought together the founding nations to develop an independent space capacity. However, Ariane 5 was still a long way away. In the 1970s, NASA developed the Space Shuttle, a reusable launch system that was designed to radically bring down the cost of launching satellites. It was an engineering masterpiece.
There was this old idea of an aircraft going so fast and so high that it would get into orbit, and it became the shuttle. But the thing is that I was there in Houston when they were launching the shuttle idea, and we had endless conferences about that, and people saying the shuttle is going to be a mix between the best of the rocket and the best of the aircraft. And the end result was that the shuttle was a fabulous mix between the worst of the rocket and the worst of the aircraft.
When they did the space shuttle, in their opinion, it was such a revolutionary machine, which should be able to fly every day, and for negligible cost, so cheap, just to use and so on and so on. And so they came and told us, so, but stop your Ariane 5, it's useless. Just come and work with us in the space shuttle. And we said, oh, sorry, but we like our autonomy, and okay, our launcher may be conventional, but we think it has some future. It paved the way for the huge success of Ariane that we still have today.
The Europeans decided that there was a market. What does the market want? What does the market need? And they found out that everybody in the world was waiting for the age of telecommunications to arrive. And so they developed the first model of Ariane, and they evolved it into different new systems, which were only beefed up versions of the basic philosophy, up to Ariane 4, which was probably the most extraordinary of them all in terms of delivery, in terms of cost per kilo to orbit.
Demand for the ability to launch satellites into space was literally skyrocketing. The Ariane family of launchers evolved throughout the 1980s, together with the telecommunications and observation satellite markets. By 1990, the Ariane 5 was well on its way to being the workhorse of commercial rocketry. This is the so-called cathedral, where the Ariane launchers are assembled. It is here that the mystery of spaceflight becomes solid engineering. Hervé Gilbert is the chief technical officer of the company that actually builds the rocket, Ariane Group. He is here to oversee an event that is rarely filmed: a central cryogenic stage being loaded into a container for transport to the launch pad at Kourou in French Guiana.
We are in our final assembly line in Europe. This is the building named Building 60 in Les Mureaux, where we assemble the main cryogenic stage of our Ariane 5 rocket. This stage, you can see it behind me. We are very lucky today because we are moving one stage from the building here towards Guyana, so it will be put horizontally in the coming minutes. This stage from here is shipped to Kourou, and there in Kourou we finalize the assembly with the other stages that will join it and constitute the final launcher.
No less than 4 cryogenic main stages of the Ariane rocket are under assembly here today, and the industrial work involves riveting and subsequent cleaning of the rocket bodies, followed by the insertion of the engines and piping, fuel tanks and turbopumps that turn these massive steel cylinders into rockets. It can be a noisy process. The key parts of the central stage that is ready for delivery are enveloped by purple covers, and each moving part is blocked by pins that hold them in place. The rocket will not be launched until every single purple element, cover and pin has been removed and visually accounted for. The blue bracket over the engine is to protect it from inadvertent breakage during transport. The Ariane rocket system is incredibly complex and is made up of 5 major parts, each of which is built separately and assembled into a final launch vehicle only when they reach the launch site in distant Kourou in French Guiana. It is a production process that involves millimetric precision and deliveries to the construction site under extremely tight schedules.
So if we look at the rocket as a whole, this is a matter, at the time of liftoff, this is a matter of 780 tons, of which the 2 boosters, there are 230 tons of propellant in each of them.
You have 2 large solid boosters here, which are used to provide a very large thrust, typically 7,000 kilonewton or 700 tons for the older one. So they burn during 2 minutes and they expel 2 tons per second. So imagine we are expelling the equivalent of 2 cars through a hole which is large like this, 2 per second, okay, 2 tons per second at velocity of 20,000 kilometers per hour. So this is producing a huge thrust. This helps us really lifting from ground, getting out of the atmosphere.
If we take now the central core is composed of the main cryogenic stage, an upper cryogenic stage, and the upper part. The main cryogenic stage weighs, let's say, roughly 190 tons, of which 175 tons of propellant, 25 tons of liquid hydrogen, and 150 tons of liquid oxygen. So this is the lower part, but the bigger part of the launcher.
Of all the parts of the Ariane 5 rocket, it is the lateral boosters that give it the power to get out of the Earth's gravity and through the lower parts of the atmosphere. They are called the EAP. The boosters are the most vital element of the rocket to get it onto the right trajectory to orbit. The choice of solid fuel gives it the maximum power in the shortest space of time. The solid propellant's job is to push the rocket into the high atmosphere. But despite its apparent robustness, the rocket is fragile. The rockets are programmed to provide just the right amount of thrust at the right time.
In the solid boosters, we're using the oxidizer and the fuel, mix them together in a solid form. For the oxidizer, we're using ammonia perchlorate as the oxidizer, and we're using aluminum pulverant, really in a very, very tiny powder as the fuel, as the reducer. And so the reaction between the two of them generate the very high temperature, very high pressure, which is used for the propulsion.
Engineers have discovered ways of providing exactly the right power at the right time by modeling the way the propellant is inserted into the booster.
The very first thing that we ask to these boosters is to have a very high thrust, to get out of Kourou as fast as possible. What we do is that instead of just a pure cylindrical canal, we have a kind of star shape. Okay, so we increase artificially the surface, which is in fire. Okay, and so this gives us a higher mass flow, so a higher thrust.
The solid propellant in the lateral boosters is extremely fast burning and volatile. It provides the power to get out of the atmosphere, but also makes up 90% of the rocket's weight.
Once this star is completely burnt, then we have less surface, and so the thrust is going down. And that's very important because this is the most critical part of the flight, which we call the maximum dynamic pressure, which is the moment of the flight where the aerodynamic stresses on the launcher are the maximum. Then I burn my cylinder. So as I increase through time the size of the canal, I increase slightly the surface of the cylinder, so the thrust increases all the way until I have nothing left to burn.
As the booster's propellant burns in contact with an ever-increasing surface, so it produces more power. Starting from the top, the star-shaped section of the propellant allows it to burn fast. But when this has been exhausted, the burn slows down until, as the fuel burns and the exposed surface increases, it begins producing more and more power, the final kick to get the rocket out of the atmosphere. The two solid fuel boosters are attached to the main rocket via solid brackets that hold them in place to ensure the power is perfectly controlled. However, the main force applied to the main cryogenic stage is at the shoulders.
One could believe that the two boosters are attached to the main core via the three rods we have in the bottom part of the launcher. In fact, they are not bearing at all the loads generated by the thrust of the two boosters. What we do is that we link actually the main core and the boosters through the head of the boosters. In fact, we push the main core and the main cryogenic stage that you can see behind me, in fact, is not designed to sustain the very high loads that would come from the boosters through the rear part, but it is simply hanging between the two boosters. This is our little secret, let's say.
All the thrust goes through this here. Here we have a kind of joint, spherical joint, where all the thrust is passed. So we have a cup and a sphere, and so this takes out all the thrust in all three directions. But then, how do we prevent this kind of movement? For this, we have three struts at the bottom of the launcher, which prevents the lateral movement like this. So all the thrust goes through the front joint, and the lateral movement, are stopped by the three struts that we have at the bottom of the stage.
So here we have the shoulders, what I name the shoulders, which are between the one booster and the main core stage. And through this very little metallic part, we have 600 tons of loads which are taken over and absorbed in order to lift the main cryogenic stage. The two boosters are bearing, pulling the main cryogenic stage through this very, very little metallic part.
The booster is equipped with an orientable nozzle made of carbon fiber to withstand the massive temperatures and pressures developed at its mouth.
When we design the launcher, as we are doing for Ariane 6 today, we take care to have a capacity which is in the range of 5 to 7 degrees, not more than that, for all the nozzles, for the boosters and for the main cryogenic stage. Practically speaking, in flight, it is very, very seldom the situations where we have more than 2.5 degrees of gimbaling are very seldom. But we size it for 7 degrees most of the time.
The main body of the Ariane is made up of a huge cryogenic engine. The Ariane 5's engine is called the Vulcan, the god of fire, in French. Although the principle is very simple, the actual workings of the rocket engine are extremely complex. The cryogenic engine used on the Ariane rocket is a formidable tool for getting satellites into space. Its workings are amazingly complex.
The cryogenic engine is a fantastic machine. This starts with a small gas generator which takes liquid oxygen and liquid hydrogen from the tanks on the launcher in order to generate a flame, gases which are exhausted at a very high speed, to put in rotation two turbines, the liquid oxygen turbopump and the liquid hydrogen turbopump. These two turbopumps are also fed with liquid hydrogen and liquid oxygen, and they push that amount of fluid into a thrust chamber, into an injection plate, which is the entry of a thrust chamber.
We are pumping hydrogen, so the hydrogen liquid hydrogen has some specificities. First of all, it's so lightweight. It is 14 times less dense than water. So you have the impression of pumping air. So for this you need to have very, very high performance turbopumps going very fast in order to pump as much as possible. So for instance, the turbopump of the Vulcan engine on the hydrogen side is something of the size of a microwave oven, if you want. And it has the same energy as 2 TGV trains, 2 fast trains. So it's very, very, very impressive. So you have one turbopump for hydrogen, one turbopump for oxygen. And so from the outlet of those, you inject into the combustion chamber.
The propellants are composed of a highly combustible element. In this case, hydrogen and an oxidizer that causes the combustion, oxygen. In order to store them in liquid form, they need to be frozen to below -200 degrees centigrade. The two liquid gases, however, will not mix by themselves. They need to be pushed together through pipes and injected into the combustion chamber at exactly the right speed. This is the job of the turbopumps. However, these are actioned using some of the energy produced by the combustion. So to get them working, liquid helium is pumped from these spherical tanks into the main fuel tanks to push the oxygen and hydrogen through the turbopumps into the combustion chamber to ignite. Calibrating the pressures is extremely complex. Bringing all the pieces together to build an Ariane 5 is a remarkably complex operation. The main stage is completed here in Les Mureaux, but the Vulcan engine is built in Vernon in Normandy, while the boosters are made in Bordeaux, and the third stage in Bremen, Germany. The turbopumps for the engines are made in Italy. Bringing all this material together and making sure they all fit is a complex operation and requires months of checks and tests.
Parts are coming from Germany, MT Aerospace in Augsburg for the upper skirt. parts are coming from Les Mureaux here. The company which is just beside me here is delivering the tanks together. Then we have below the tank, we have a thrust frame which is coming from Netherlands, and then the engine, the Vulcain 2 engine, is coming from Vernon in France. Most of the time we take in this final assembly line is with checks of tightness, checks of electric continuity, electric isolation, and so on. This takes 9 months, whereas the mechanical assembly is a matter maybe of 1 week, not more than 1 week.
We use our third stage, which is here, which is also a cryogenic stage. Hydrogen, oxygen, liquid. We have 15 tons of them, propelled with an engine which is called the HM7B, okay, which is and so this one guarantees it works during for 20 minutes roughly, and gets all the way to orbit. And so once it reaches the proper orbit, then it is automatically cut.
While the main parts are made in France and Germany, with the payload fairing coming from Switzerland, the final rocket is assembled on the launch site at Kourou in French Guiana, where the solid fuel is mixed and molded for insertion into the boosters, and, as a very last stage, the cryogenic liquid fuels are loaded into the central and second stages. Kourou, French Guiana, is a tropical paradise. But most people come here not for the beaches, but because of its latitude. This is an ideal place, close to the equator, to launch a payload into geosynchronous orbit. Here, vital activities complete the production process of the Ariane 5 rocket. This is where the boosters are filled with solid fuel, and where the liquid gases, hydrogen, oxygen, and helium, are loaded into the tanks. The ground infrastructures are massive, and the launch pad is designed to survive the huge thrust provided by the rockets and the cryogenic engines. This is where the weather is monitored, the winds especially, that can cause a mission to be delayed or even aborted. This is where the control room follows every second of pre-flight activity, and where the computers that control the flight are located. It is a massive infrastructure owned and run by the French space agency CNES.
5, 4, 3, 2, 1, top. Allumage Vulcain, allumage des deux EAP et décollage vers 244.
As the rocket hurtles through the air, out to sea at first and then up into the stratosphere and into space, the fuels in the boosters and the first stage burn up. The boosters are jettisoned and fall into the ocean. They are reusable and are recovered in the Atlantic, while the first stage accompanies the payload into space and then falls back to Earth once empty and burns in the atmosphere. The second stage kicks into operation, taking the payload fairing to the height required. Once the rocket has been launched, the most complex part of the mission is yet to come: controlling the rocket and pushing it onto the right ascent path.
A launcher such as this one is very unstable. What means unstable? It's just like a pencil on top of your finger, and you really need to try to keep it vertical. It's very complex. You need to move very fast. Here, it's even faster. You need to react every 70 milliseconds. Otherwise, you lose it. Otherwise, you don't control it. It flips back, and then it's destroyed. And so what we need to do is to control it real time, very, very fast. So it has to be done on board.
At any point in time during the trajectory, the onboard computer is evaluating the current position and the trajectory that should be followed. This is guidance. Navigation is providing the instantaneous location. The most fascinating part probably is the control of it. So by steering the orientation of the nozzles, so steering the orientation of thrust and getting the counter reaction of the body which accelerates, we take care, in fact, to put it on the trajectory that has been determined by the guidance, knowing that by nature such a launcher is fundamentally unstable.
There are different kinds of orbit, and since the Ariane is able to carry 2 satellites, a dual payload, the final stage with the payload fairing is sometimes required to move from one orbit to the next.
So on Ariane 5 we launch typically 2 satellites, one big one which is in the range of 6 tons in the upper position on the launcher. Then there is an intermediate structure which looks like a bell. So the upper one is put on the bell, and there is a smaller one, 3 tons and a half on the lower position under the bell. So this is the performance of Ariane 5, 10 tons roughly for the geosynchronous transfer orbit. Okay. Ariane 6 will be a little bit better by 1 ton, typically 1 ton more, which will be allocated both to the smaller one and to the bigger one.
Today, the average size of a satellite, of a geo satellite, is 5 tons at launch. So 2 of them, we need 10 tons. And so this dictated the performance of Ariane 5. We set a record, a world record, very recently with 6.3 tons on one satellite. And we have some satellites at up to 8 tons.
This is the most delicate phase of the mission. It is the moment when the value of an object launched into space comes into its own. The make or break moment of the launch comes when the final stage pushes the payload into its final orbit. The last stage, which holds the payload fairing, is powered by a highly flammable and toxic fuel called MMH hydrazine.
Where we very often aim at is what we call low Earth orbit. So low Earth orbit are roughly up to 2,000 kilometer altitude. This is very used for all the observation missions. This is one of the key market, all the low Earth orbit for the observation, for environment, for meteorology, and so on. Then if we move on, we have at roughly 20,000 kilometers from Earth. Here we have the GPS satellites, the Galileo, and their equivalent. The most useful orbit is the GO, Geostationary Earth Orbit. Geostationary, it means it's an orbit where a satellite, when placed there, is always seen as fixed from any observer from the ground. That's 2/3 of the commercial market today.
Apart from launching thermonuclear weapons, the only goal of rocket building is to launch satellites and modules for the International Space Station. Communications satellites may cost millions to make, but over a service life of decades, and with the spread of radio telephony, they will pay for themselves many times over. In proportion, the cost of launching is minimal, and that cost is further reduced by economies of scale. Ariane Group's future depends on the evolution of the satellite industry. While Ariane 5 was initially developed by the European Space Agency under the technical leadership of the French Space Agency, CNES, the next European rocket is being developed directly by the constructor, Ariane Group.
There was a decision that was made by the European member states, the European governments, 4 years ago, by which we decided to group under one single umbrella, one single industrialist, the role of lead system integrator in production, which means the architect of the launcher during development and design of the launcher, and the engine manufacturers, so teams from Airbus for the first part and from Safran Group were put together in one single company, which is our company now, Ariane Group. And the decision was made that this company should be the prime contractor and the architect of the launcher.
Competition in the marketplace has picked up with the arrival of private constructors. The first launch of the Falcon Heavy in February 2018 seemed to be a turning point in Elon Musk's ability to deliver heavy satellites into space. Ariane Group has chosen a different path for the time being.
We have changed some little but big things on Ariane 6 with respect to Ariane 5. The boosters are smaller on Ariane 6 than on Ariane 5. So this is a matter of 147 tons of propellant per booster on Ariane 6. So 2 big boosters for Ariane 5 and 2 or 4 smaller boosters for Ariane 6, which gives modularity and which gives us the opportunity to launch small payloads at low altitude, low Earth orbits, or bigger payloads, even slightly bigger than the ones of Ariane 5 today, when we have 4 boosters on high altitude orbits.
Being able to modulate the weight and power of the launcher will mean that Ariane 6 will be offering a more flexible launch service. Many smaller satellites or fewer large satellites, 2 lateral boosters or 4. And above all, the final stage can be reused to position satellites in different orbits. The cryogenic engine will be improved, although the basic structure will remain the same. Construction of the rocket will be more streamlined too, and the thousands of rivets holding together the cylindrical segments of the rocket will be replaced by a new form of welding.
Another aspect is, another example I have in mind, is about the way we weld the panels that constitute the tanks. So we had quite old technique which is used on Ariane 5, because Ariane 5 has been designed in the 90s, even a little bit before the 90s. So all the welding techniques are replaced now by a safer one, a more secure one, which is named friction stir welding, and which works simply by melting the 2 parts you want to join. You melt the interface between them, and then they naturally stick to each other without any defect and discontinuity in the material.
Friction stir welding uses friction to melt 2 surfaces to weld together, and as they melt, they are pushed together to form a single surface. It is another new manufacturing technique that increases robustness and lowers cost.
What we have been doing, what we are preparing, on Ariane 6, is new ways of manufacturing. Additive manufacturing is really paying off when we are speaking of propulsion parts, parts of turbopumps, parts of gas generators on board of the engines, building these parts via additive manufacturing, which is 3D printing. By doing that, we save a lot of times. We save months in the production of these parts, a lot of energy, a lot of power supply. So there are lots of savings done here, but we keep the same material as before. We just manufacture the part in a totally different manner.
The Les Mureaux plant has been redesigned with an entirely new factory built alongside the cathedral. The Ariane 6 will be built horizontally, allowing easier access for workers. Europe deploys its own navigation system, Galileo, using the old Ariane 5 workhorse that has paved the way for European access to the growing space economy. As the rocket with Galileo aboard hurtles into space, powered by its 2 lateral boosters and the cryogenic Vulcan engine, its mission is to complete the European-owned and managed navigation and observation system. In the future, exploiting space will take not bigger rockets, but more versatility, and Ariane 6 and other rockets such as the Italian Vega attempt to stay competitive on the market.
So the first measure we have taken when observing this drastic reduction of the cost of launch service that Elon Musk has been able to do has been to develop the Ariane 6 launcher. More or less twice cheaper than Ariane 5, with a higher capacity in orbit, a higher versatility in its missions. It will be capable of many types of missions in orbit, many types of orbits, whereas Ariane 5 ECA, our workhorse today, is only capable of one type of orbits.
Born out of the French and German drive to create an independent European space launcher, Ariane 5 and 6 is a collaboration between Ariane Group, Ariane Space, CNES, and industries all over Europe. Hervé Gilbert has lived the life of the space engineer for a quarter of a century. He has had some exciting moments.
You have simulated many things. You rely on your simulators. The particularity of our business is that we never fly for tests. We fly for going to space at the first time. So the reality and the truth of everything you have modeled before flying, you will discover it during the flight, the qualification flight of your launcher. So these are fantastic moments for us, and we are really looking forward to having these moments together for Ariane 6 in 2020.
The sun sets over Kourou, French Guiana. This equatorial country, still under French authority, offers the perfect place of launch for heavy loads into space. Hundreds of space engineers and technicians work here to make this international effort successful. Another Ariane 5 is ready for launch. Another space adventure about to begin.
4, 3, 2, 1, top. Allumage Vulcain. Allumage UAP, décollage. Tous les paramètres à bord sont normaux.